Today we're going to look at this idea of locus again. Remember, all locus is a relationship between the x and the y values, although now x and y could stand for real and imaginary. So, circles. So there's a basic circle, centre of the origin, radius r. We could say z times z conjugate equals r squared, and I think I mentioned that one before. So remember, z times z conjugate is real part squared plus imaginary part squared, so we get x squared plus y squared is the radius squared. But now there's another way we can describe this, and probably a more common way, and that's simply that the modulus of z is equal to r. Remember, modulus of z, distance to the origin. So on that particular circle, every complex number that's on the circumference has the same distance to the origin, and that being the radius. So if we see modulus of z is equal to some number, we know we're talking about a circle if we were to draw it. Now the shifting idea still exists. So if I move the centre to another complex number, let's call it omega, what we saw before was we could write it as z minus omega times z conjugate minus omega conjugate is equal to the radius squared. That gets a little bit clunky writing it that way, so the modulus is better. Z minus omega is equal to r. What is that saying? If we combine it with the idea of vectors that we looked at yesterday, z minus w, have a look at the radius that I've drawn in. Now everywhere on the circumference is a possible z. If I was to join it up to the centre, I get this vector. We said vectors were head minus tail. So z minus omega, absolute value, or the length of, we're saying the length of that vector is r. So again, we get a centre. This is that instead of joining up to the origin, we're joining it up to another complex number. So another complex number would be the centre. So modulus of z, or modulus of z minus some complex number, equals a constant. We know if we were to draw it, we get a circle. So we're going to express these circles, but we're going to rewrite it in terms of the complex number z. So we'll start off with a very simple one. X squared plus y squared is 16. So we're saying the real part squared plus the imaginary part squared is 16. We now know we can simply say, oh well, modulus of z is equal to 4. Just be careful. The 16, remember, is radius squared, and that's what we're used to doing. But when we're doing modulus, we're saying the length of the vector. So it's not r squared, it's just the radius. So it's 4, not 16. If we were to write it in the terms of the conjugate way, that one would be z times z conjugate is 16. The modulus way is probably the more common of the way of doing it. Oh, so this one here, well, its centre's been shifted. We're going to have to complete the square to find out where it's been shifted to. So x squared plus 6x, we'll group the x's together, y squared minus 4y, move the 12 to the other side. To complete the square, we add half the coefficient of x squared. So we have 3 squared and negative 2 squared, which is 9 and 4, and we add that to the 12, we get 25, and we have x plus 3 squared plus y minus 2 squared. So we now know we're joining it up to where we've shifted it to, 3 and negative 2i for the imaginary part. So the actual centre would be negative 3 plus 2i. So it's always z minus the centre. And the length of that vector would be the radius, which is 5. If we were to write it in the conjugate form for some insane reason, that's how we would write z plus 3 minus 2i, and that would be times by the conjugate. So conjugate of z plus 3 plus 2i, and in that form it is radius squared, so 25. Let's go back the other way. We've got to find the centre and the radius. This time we're talking about the modulus of z minus 5 minus I. So we're joining the vector z up to 5 plus I. So it would be the point 5, 1. That's the centre. the length of that vector is 2 units. Here's one in conjugate form, but it is okay, it is the correct form. So it's z plus 4 plus I, conjugate of z plus 4 minus I. So we've got the form that we want, the number, then in the second one the conjugate. So the centre for this one would be minus 4 minus 1, and when it's in that form it is radius squared. So the radius would be 7. Radius would be 7. The modulus of 3z is equal to the modulus of z plus 2 minus I. So what is this saying? I could factorise the 3 outside of the modulus of 3z. Remember, it's the same as absolute value. They're like grouping symbols, and I know the absolute value of 3 is 3. So I could factorise that out. It's not immediately obvious to me. So if that's the case, let's go back to Cartesian form and find the equation. So, as I say, I could factorise 3. Okay, modulus of z, real part squared plus the imaginary part squared. And then on the other side, I've got the real part squared, x plus 2 squared, plus the imaginary part squared. Notice I've squared the 3. You remember, modulus is the square root of. So I've got rid of the square root signs by squaring both sides. But that means I have to square the 3 as well there. Okay. Expand the right hand side out. Let's group some things. It's looking like another circle, because the coefficient of the x squared and the y squared are the same, and that's what we expect with a circle. Let's divide everything by 8. I prefer to complete the square when I've just got 1x squared and 1y squared. I find that easier myself. So half the coefficient of x, half the coefficient of y. Well, it's ugly, but we have ended up with a circle. X minus a quarter squared plus y plus an eighth squared is equal to 45 on 64. So we know it's a circle. Its centre is a quarter minus 1/8. Its radius 3 root 5 on 8. So if you look at it, you can think about it for a little while. If it's not coming to you, put it back in a Cartesian form, and then hopefully you'll recognise the equation from that. This time we've got conjugate. So z times z conjugate plus 2 times z plus z conjugate is equal to 0. Again, not immediately obvious. Okay, so z times z conjugate. Well, z times z conjugate, x squared plus y squared. Z plus z conjugate is twice the real part, and the real part is x. So we're going to have x squared plus y squared plus 4x. So yes, indeed, it does turn out to be another circle. Complete the square, and we've got it there. So centre minus 2, 0. Radius 2. Right, so circles. That covers our circles. It's basically modulus of z equals a constant number, circle. Lines. Well, we talked about this one the other day, but just to recap, horizontal lines would be the imaginary part of z is equal to a constant number, because the imaginary part of z would be y. So we've got y equals a constant horizontal line. Vertical line, real part of z, because the real part of z is x. X equals a constant, we'd get a vertical line. But what about ones that are not vertical or horizontal, but at some angle? Okay. In terms of complex numbers, there we go. I've just drawn in a couple of other things there. I've drawn in W1, W2, and I've placed it in such a way that that line becomes the perpendicular bisector. Okay? Now, any line we should be able to do this with. So what we're now basically saying is, remember, on that red line are all the possible z's. We're saying if we join z up to W1, the length of that vector will be the same as if I join z up to W2. So we're saying modulus equals modulus. We're saying the lengths of these vectors are the same. Now we could easily prove that using similar triangles. You've got a right angle there. We know that those sides are the same, and then you have a common side. So side angle side, sure enough, they would be equal. Now, why is it convenient to know it's a perpendicular bisector? Well, if you know what W1 and W2 is, you can find the midpoint. You can find the slope of the blue line, but then once you know the slope of the blue line, you know the slope of the red line, because it's perpendicular. So you do negative inverse. So it gives you another way of finding the equation. So let's have a look at this one. I see modulus equals modulus. And it's z minus one complex number z. So we're talking two vectors here. We're saying the length are the same. I see that and I know, right, we're talking about a straight line. That straight line is the perpendicular bisector. Now, if I didn't recognise that, of course, if you forget that idea, again, you could always go back to Cartesian form. So if we take it back to Cartesian form, let's do that first. X minus 1 squared plus y minus 1 squared for the left-hand side. X plus 2 squared plus y plus 1 squared. And obviously I've squared both sides to get rid of the square root sign. Expand that all out, and you'll notice the x squareds and the y squareds cancel out, leaving me with a linear function where I've just got y's and x's. So tidying it all up, there it is, 6x plus 4y plus 3 equals 0 would be that line. I mean, that's pretty quick in itself. So I'm not dismissing that as a method. It doesn't take too long. The other idea, perpendicular bisector. Now the points would be 1, 1 on the left-hand side, negative 2, negative 1 on the right-hand side. Perpendicular bisector, so I need the midpoint. Turns out to be minus a half, 0. I need the slope. Well, the slope joining our 2 points is 2/3. So the one I want is negative 3 on 2. I've got a point, I've got a slope. Put it into the point slope formula, and we come up with the same equation. Now you might be looking at that and thinking, well, hang on, that looks like more work to me than the first one. And possibly for this one it was. If I get a question like this, notice it doesn't actually say find the equation. It simply says sketch. So if I remember that it's the perpendicular bisector, I can draw this real quickly. I don't have to find the equation of the line. So I can go, righto, z plus 2i, so that's negative 2, and z minus 4i turns out to be a horizontal line, because it's going to be the perpendicular bisector of 4 and negative 2. Halfway between 4 and negative 2, there it is, 1. Perpendicular bisector. I've answered the question. I've sketched it. It's never actually asked for an equation. Mind you, now that I've sketched it, the actual equation you can see would be quite easy, because we're talking about a horizontal line. So make sure you read the question, I guess is what I'm saying. Is if it doesn't ask for the equation, you don't need to waste time. You can, if you know what it looks like, draw it. Draw it. Okay, the rays. Who remembers what a ray is? The ray has a definite starting point, but then just keeps going in a direction. We now have something that describes that. There it is right there. So there's a ray. This one's starting at the origin to start off with, going off in some direction. That direction we can define by the angle it makes with the x-axis, or the positive side, which we know to be the argument. So every point on that ray, the argument of every complex number would be theta. That'll be what they have in common. So we see argument of the complex number, or z, equal to an angle. We're talking about a ray. But again, it doesn't have to start at the origin. It could start anywhere. So I've just drawn a dotted horizontal line. The angle it makes with the horizontal, if we join z up to that starting point, that angle will always be theta, no matter where we place z. You'll notice I've circled the starting point. And that's to show that the starting point is not included, because you can't find the argument of a single point. It's only once you head off into a direction that you can say what the angle is. Right? So you always exclude the starting point of the ray. Now we have a different way of describing shading regions in the plane. We're going to draw this one. The modulus is less than 1, and the argument, we want all the complex numbers such that that is true. Well, the first one's going to give me a dotted circle, because it's just less than, and the radius would be 1, and in this case I'd be inside the circle, because we're saying all the points such that its distance to the origin is less than 1. So I'd be inside the circle. But in addition, all of these points must have an argument in between 0 and pi on 4. Pi on 4, or 45 degrees. Technically, I should have dotted once I got past the circle. Because remember, the solid line means it's included, but we're saying it has to be inside the circle. Now, of course, it's a bit hard to do that with PowerPoint. Get the line and go solid, 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 dot, 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 dot. So that should be dotted after the circle. And equals 0 would be going off to the right. So similar thing, it should be dotted after the circle. And we're talking about that little sector in there. So all the points in that sector there would have a modulus that's less than 1, and an argument between 0 and pi on 4. There's one other thing I should do. Well, when you're talking about regions in the plane, if you have a dotted line meeting a solid line, the point of intersection is not included. As soon as one of the boundaries is not included, the point of intersection is not included. So I should also exclude those 2 points there. Okay. Well, quite a few little exercises there to do. Well, little 1, A, C, 2, B, D, 3, 4, 5, 6. Yeah, they're little. Remember what I said yesterday. Friday, I'm not going to do any theory on Friday. Okay? So I'll do another bit of theory tomorrow, but we got through